time, we spent a lot of time talking about options pricing using the name-only asset pricing model. Basically, the idea that you have this option, this ability to buy or sell a commodity at a fixed date at a certain price, and then you pay some ability for that option. This is the idea that having optionality is worth something. Now we're going to talk about a continuous time pricing model. So before we assumed a discrete time that prices move in specific ways in discrete increments. Now we're going to assume continuous time. We assume a Brownian motion models the random movement of the particles, or in this case, the asset. So this was originally developed. There's some debate. Most people credit the biggest movements in Brownian motion to be early work in physics done by Einstein and other physics around the turn of the 20th century. But actually, there's a lot of work done on Brownian motion and continuous time stochastic processes by a French finance theorist, even in the 1870s. He unfortunately did not get his PhD in mathematics because he was not seen to be doing something that was considered real math, because back then finance was not considered to be a legitimate portion of math, but later on a physicist dug it up and found it to be just a spectacular description of continuous time movement. So the continuous time stochastic process with key properties, first off, these independent increments. Movement in non-overlapping intervals are independent. Stationary increments, the probability distribution of movement depends only on the length of the time interval, and increments are assumed normally distributed. This is used to model asset price movements in the financial markets. Remember, I'm not testing on any of this. I don't say you know this for the class, but it's useful to know in general and have heard of these terms. So let W of t represent a Brownian motion process where W of 0 equals 0, Wt minus Ws, the price at time t minus the price right now is approximately normal with mean 0 and variance, the amount of time remaining. The variance you expect between for the price at the time t and the price now is directly based on how much time is left. So the variance is decreasing until time is up, with variance going to 0 as time goes to 0, and Wt has continuous path almost surely. So remember that the expectation of Wt equals 0. This is the option, if it's fairly priced, is expected to have 0 value, and the variance of the option is t. The variance of the option is proportional to the amount of time the option has, and this serves as the foundation of modeling prices for random movements. So geometric Brownian motion for asset pricing. My prices are modeled using geometric Brownian motion. D of s, the derivative of the commodity price at time t, is equal to the expected return, or the drift coefficient, times the commodity price at time t with derivative with respect to time, plus the volatility of returns times the commodity price at time t times the derivative of W, or the increment of Brownian motion, because remember, we're assuming Brownian t reflects a Brownian motion process, and S of t changes over time. So we're modeling how the prices move. The geometric Brownian motion process ensures that prices remain positive and models potential for exponential growth. And so Black-Scholes, which is the standard option pricing model, was developed by Fisher Black and Byron Scholes in 1973. Merton also developed this theory independently, but Black and Scholes won the Nobel Prize for it because Merton, I believe, had perished before the Nobel Prize was given. And it provides a closed form solution for pricing European options. It assumes that the underlying asset follows geometric Brownian motion, which we just talked about, and it's key for understanding option pricing commodities in financial markets. So the price for a European call option, this is very similar. You should remind you of how the binomial asset pricing option works. C equals S of 0, the current commodity price, times N of D, which is the cumulative distribution function of standard normal distribution, minus the strike price times, here's this before the exponential raised to the negative of the risk-free rate and the time to expiration, and then times N of D2. So this is the cumulative distribution at the start, and this is the cumulative distribution at the end of the probabilities. So D1 you can calculate at using this formula. I won't get into. D2 you can calculate using this formula. If you're interested in exactly the derivation of this formula, I encourage you to look it up and read about it. But just know that while you can price assets in discrete time using the binomial asset pricing model, you can price them in continuous time using the Black-Scholes formula. And so the price of a put option, this was the price of a call option. The price of a put option should be different because you have a different exposure. And so this is based on because in a put option, you are selling an asset, so you want the price to be lower than the price you're allowed to sell it at. So that here you want the strike price to be lower, and you want it's based on the probability that the price moves in your favor, meaning the price moves down. Parameters D1 and D2 are the same in the call option formula, and it reflects the right to sell commodity at the strike price K. And obviously, as you get closer and closer to the time of maturity, the price will converge to the difference between the current price and the strike price, unless the option is out of the money, in which case the price converges to zero. I should mention one more thing. The risk of an options contract is the price that you pay for it. So you're having to pay to buy this contract, which is why there's a price. And this is just lost money. So that's the risk of buying the option, is always how much you pay for it. So whether or not you should be out of the option is based on whether or not you believe that the risk is greater than the price you're paying for it, and the price you're paying for it provides an level of insurance that you believe is desirable. So assumption of the Black-Scholes model, markets are frictionless. Obviously not the case here in commodity markets where there's a lot of friction, but still good model. The risk-free rate is constant over the option's life. The volatility is constant known. Commodity prices follow a continuous time geometric Brownian motion with no jumps. There's a pretty significant argument that there's a jump diffusion process going on here if you look at long-term commodity series, particularly in the short term. But if you look at like a 30-year series, you're going to see some jumps. But it's smooth if you don't look at the immediate trades, but only look at a really, really long series, and you can dismiss the jumps because on the long term is smooth. It assumes that no arbitrage opportunities exist, so all assets are correctly priced, and that options are European style and exercisable only at expiration. So the application to commodities markets, commodities often exhibit mean inversion symmetry, challenging the geometric Brownian motion assumption. Part of the value of knowing about Black-Scholes is knowing if the prices don't look like this, why not? And the commodity markets have some particular values that challenge the assumptions, and adjustments can be made to the model to account for these, to account for stochastic volatility, mean reverting price processes. You can use Ornstein-Ulbeck processes to deal with mean reversion. And you can look at how convenience yield feeds into commodity prices. Despite the severe limitations, it provides the baseline Black-Scholes for commodity option price valuation is still quite heavily used in the market. Here's a numerical example, just a quick numerical example to close us out. The current commodity price is 50. The strike price is 55. The interest rate is 5%. The risk-free interest rate is 5%. The standard deviation is assumed to be 20%, and the volatility rather is assumed to be constant at 20%. Time to maturity is 1 year. Plug in ln of 50 divided by 55 plus 0.05 plus 0.5 times 0.2 to the second times 1 divided by 0.2 square root of 1, and so d2 equals d1 minus 0.2 minus square root of 1, and then you use these from the standard normal distribution tables. You calculate based on D1 and D2, you calculate N of D1 and D2, and you compute C and P using the Black-Scholes formula. So limitations and extensions, it assumes constant volatility in interest rates, which are not true across time, so you have to work with that. Does not count for sudden price jumps or spikes, and that's actually accurate for longer dates. There are various ways to fix this. I hope If you're interested in this, you look into it further. Otherwise, this is just a digression so that you're aware of how assets are priced in continuous time. I hope you have a great day. Thank you.